If you get hold of two magnets and you push them, you can feel this pushing between them. Turn it around the other way and they slam together. Why are they doing that, or how are they doing it?
You're asking...
I must say, I think that's a perfectly reasonable question.
Of course it's a reason. It's an excellent question. Okay. But the problem that you're asking, you see, when you ask why something happens, how does a person answer why something happens? Now, when you ask, for example, why two magnets repel, there are many different levels. It depends on whether you're a student of physics or an ordinary person who doesn't know anything or not. If you're somebody who doesn't know anything at all about it, all I can say is that there's a magnetic force that makes them repel, and that you're feeling that force. I'm not answering your question, but I'm telling you how difficult a why question is. You have to know what it is that you're permitted to understand and allowed to be understood and known, and what it is you're not. Well, I'll just have to tell you that's going to be one of the things you'll just have to take as an element in the world, the existence of magnetic repulsion, or electrical attraction, magnetic attraction. I can't explain that attraction in terms of anything else that's familiar to you. So I'm not going to be able to give you an answer to why magnets attract each other, except to tell you that they do. But I really can't do a good job, any job, of explaining magnetic force in terms of something else that you're more familiar with, because I don't understand it in terms of anything else that you're more familiar with.
The mathematicians tell you that a magnet's field is comprised of lines of force. However, they immediately clarify that these lines are merely abstractions, solely used to represent the forces surrounding a magnet. So, what entity mediates the forces in a magnet in the alternative if these lines are not real? What is it that is moving when they assert that the lines travel through the inside of the magnet? The answer is that the mathematicians pretend to do physics with absolutely nothing, with magic. This is the reason they become a little uncomfortable when you ask them to explain how a magnet works. In physics, however, all phenomena must be and are mediated by objects. We can't do physics without objects. All physicists learn this principle on the first day of class. Those who do physics with abstract concepts and pretend to move them around have never taken a course in physics. We begin by establishing that all atoms in the universe are interconnected. Under this proposal, the abstract mathematical lines of force are actually three-dimensional threads that extend from one atom to all others. When a row of aligned atoms spin, they swing the threads around themselves in the same direction. These threads sweep around the outside of the magnet and through its middle, here illustrated with red lines. The mathematicians refer to the end of the magnet where the threads come out as the north, and to the end where the threads come in as the south. However, a magnet is not divided into north and south. It is physically divided into top and bottom. If the threads in the top half of a magnet swing clockwise, the threads of the bottom half swing counterclockwise. Mother Nature does not understand north and south or positive and negative. Mother Nature understands clockwise and counterclockwise. It is thus that when the south end of a magnet faces the north end of another, The threads on the top half of the south side swing clockwise, while those of its bottom half swing counterclockwise. Likewise, the threads on the top half of the north end swing clockwise, whereas the threads on the bottom half swing counterclockwise. When the threads of the top of the south side come down, they drag the threads of the top of the north side, which are coming up. Conversely, the threads of the bottom half of the south side come up and drag the threads of the bottom of the north side as they come down. To visualize this mechanism, think of two people skipping ropes close to each other. The rope of one comes down and that of the other goes up. The ropes pull on each other. The closer one magnet is to another, the more threads that intervene in the entire process, and the stronger the pull of one magnet on the other. If we turn one of the magnets 180 degrees sideways, nothing changes. The same pattern develops and we continue to have attraction. However, if we turn the same magnet 180 degrees from front to end in the north-south direction, now the top threads and bottom threads of both magnets are clashing against each other. Think of two people skipping ropes against each other. The ropes will push each other away. It is these rapidly moving walls of threads which create attraction and repulsion between magnets. Now you can explain how a magnet works to your friends. My name is bgaede, and I'm a very famous nobody, and I want to keep it that way today. Hopefully all of you came here not to ask for my autograph, not to ask for my credentials. Hopefully all of you came here to ask for an explanation of some phenomenon of physics. And maybe that's what we should ask all these people like Stephen Hawking, or even if you meet Einstein on the street someday, you don't ask him for his autograph, you ask him for an explanation. You don't care who the guy is. Can he explain some phenomenon of physics rationally? That's the issue. And that's what we're going to do today. I'm going to be explaining today one phenomenon. I'm going to explain how a magnet works, how a magnet attracts another from a distance, and how it pushes it away. I'm going to explain the mechanism. I'm going to give you a physical mechanism that you can take to your friends, to your family, and say, hey, I can tell you how a magnet attracts another. Now, I chose this subject because it's like it's the test of fire. It's called the lion's paw test. Lion's paw in the 17th century, there was a mathematician, his name was Bernoulli, and he had a problem he could not solve. And so he sent it to different minds in Europe, and he says, please solve this problem for me. One of the answers came back from Muriel England, and it was anonymous, no name to it. And so Bernoulli got it back. He says, this is the right solution.
And he says, who sent this? He said, we recognize the lion by his paw, thus the lion's paw test. And he was referring to Newton. He said, the only guy who could solve this problem from England is Newton. And so it's called the lion's paw test for mathematics, and this is the lion's paw test for physics. Physicists, we learned this on the first week of physics. If you don't know, you can't explain in a rational way how a magnet attracts another, you haven't taken your first course of physics. Now, someone might come and say, look, I've got a degree in physics from, Oxford University. Oh, yeah, that's fine, but, it's like, does that make you a physicist because you got a degree? Let's say you're running a circus, right? And you put an ad in the newspaper, wanted tightrope walkers.
Oh.
And this guy shows up. You're a tightrope walker? Yeah. Okay, there's a rope, walk it. So the guy gets up there and starts, takes one step and falls. Okay, he tries again, takes a step, falls. He does this 10 times, and he always falls. And you say, I got a show to run tonight. I thought you said you were a tightrope walker. Well, I am. See, I've got a degree from Ringling Brothers Barnum and Bailey Circus. Oh, geez, yeah, your credentials are very impressive, but you can't walk a rope. So you're not a tightrope walker. And this is something similar. We learned this on the first week of physics class. If you don't know this, then you haven't taken your first physics course. You might think you're a physicist. You might have the degree from the best university on the planet, but this is the test of fire. Can you explain how a magnet attracts another? And that's what we're going to do today. I'm going to show you how a magnet does it, what the mechanism is. Okay? But before that, we have to find out what physics is. What is physics about? Physics, first and foremost, requires an object. You cannot do physics without an object. Imagine we take, I brought it here, magic wand. And we erase all the matter from the universe. We take out all the galaxies, all the stars, all the planets, all the gases, every atom. There's nothing there. Poof, we did it. There's nothing. Well, there's not much going on in such an empty universe. What's happening? What do you see happening? There's nothing there. In order to see something happening, you need to have some kind of object in there moving, doing something, flashing. You can't do it with nothing. So let's put something in there. We're going to put love in there. Can we do physics with love? Can I just pour some love in there and have it crash, move around, do things, rotate? No, we can't do physics with love. Why? Because it's a concept. I can't move love. I can't talk about the motion of love. Maybe of a heart, but not of love. Okay, so let's put something else. Well, let's put energy. Can we do physics with energy? Is there such a thing as energy that we can move, transfer, kick around, turn into mass? Is there such a thing? Energy is defined as the capacity to do work. It's a concept. I can't move energy around because there's nothing there to move around. It's defined as a property of objects. It's a concept. I can't do physics with love. I can't do physics with energy. You need an object. So what is an object? Well, it turns out in the last 200,000 years, since we descended from the trees, I guess, no one has defined what an object is. Nobody knows what an object is. Not a single book of physics. You go to high school, you go to college, not a single book of physics begins by telling you what an object is. Here we have the first rule of physics. It says you can't do physics without an object. And no one has ever defined what an object is. So we have to define what an object is before we can do any physics. It's the first word any physicist has to define. And we're going to define that as that which has shape. That's what an object is for the purposes of physics. Now you won't find that definition in the dictionary. If you look at any dictionary anywhere in the world, an object is defined as that which we can touch or see. The problem with that definition is circular. We can't use it in physics. Something else has to do the touching, something else has to do the seeing. You need an object to define the word object. So it's circular. We can't use that. This definition stands on its own. You don't need to touch, do anything. You don't need to run a proof, an experiment. If an object has shape, if it's the only object in the universe that has shape, it qualifies as under the word object. Anything else that doesn't have shape falls under concepts. We have concepts, we have objects. So we're going to be doing physics with objects here. And what we're going to do is explain magnets. Here I have two pieces of metal. Two chunks of metal. That's all. This is the entire system. And I put them together, and they stick. Magic. Magic that very few people can explain. They said, how does it happen? You know, it happens from, I can feel it pulling right there. Anyone can try it at any time. If I turn them around, I get the opposite effect. I can't put them together. They push each other away. Here I have two horseshoes. They're made out of metal too. And I'll do it here so it won't fall, but you'll see that, you know, it doesn't hold on. You know, it just falls off. There's no magic here. So here we have magic, and here we don't have the magic. There's some qualitative difference here. Something different between this set and this set. And hopefully it's mediated by an object. Well, we're all crazy. What are we going to do it with? We're going to do it with nothing? With concepts? Is a concept holding these two, you know, U-shaped or horseshoe-shaped magnets together? What's holding this? There's nothing there. Something's different between this set and this set. And we have to explain that difference. What is the difference? You know, are we just going to describe and say, they stick together, north attracts south? Well, what does that mean? I could have said Y attracts X. Have I explained the mechanism? No. I need to explain the physical mechanism of how something attracts something else from a distance. It's already pulling on me right there. So this is what we're going to try to explain, what's happening in there. And what we have to do is identify the object that's doing that magic. Now, these two sets and these two sets, they're both surrounded by objects. An object is that which has shape. Now, both of these objects are surrounded by air. Some people don't realize it, but air is an object. It's not a concept. Air is made out of atoms, which turn into molecules, O2 and some other stuff. We call it air. You might say, well, what is the shape of air? I mean, if an object is that which has shape, and I'm saying that air is an object, well, what is the shape of air? You might ask that, right? Let me show you the shape of air, at least on our planet. This is the shape of air. Air covers our planet. It's made out of atoms. It looks like a shell. That's what air looks like here on our planet. But you can give it any shape you want. You can take a balloon, blow it, could be a sphere. Astronaut takes the balloon to outer space, pinches the balloon, and the blob comes out. Some irregular blob comes out. If you could color code it, you could see it. You could say, oh, there's air. It looks like this blob. So the question is not what is the shape of the blob. The question is, does it have shape? It's a yes or no type of question. You know, energy, does energy have shape? We're not asking what is the shape of energy, is does it have shape? And the answer is clearly no, it's a concept. Concepts do not have shape. On the other hand, you know, objects do have shape, and here air has shape. It can take the shape that you want. You can mold it into anything you want. But see, these two systems, they're both surrounded by air. They're both surrounded. So air is not the one producing the magic. There's some other object that we cannot see here besides air that's doing this magic. That's what we've got to identify. So what is it that we want to explain? We want to explain several properties that lead to magnets. We have to explain every one of these properties. We cannot just explain one and say, oh, we discovered how magnets work. We have to explain each one of these properties. Let's go with the first one. This is a wire, and the conventional wisdom is that we have electrons, the negative little balls there, they're flowing. And just by the flow of these electrons, it creates what is known as a magnetic field, those rings you see around that wire. Okay, everybody see that? So just by the flow of electrons, this is the explanation we received today, a field is created. This field extends beyond the wire. It's a halo that surrounds the wire. If you got close to that, you know, you could put a magnet close to that, just like this one, and you could pull the wire without touching it. You know, at some point, it gets close enough to the halo that the wire is pulled in. So it's something physical there. You know, this is not nothing. This is something. That ring around there. So we have to explain, what is that ring? Any theory that talks about magnetism has to explain that magic. What is that halo that surrounds a wire? Next property we have to explain. These are all observations that we've seen for many years. We turn the wire, that wire, and you can see that this is called the left-hand rule. This is the direction of that field. It's called a magnetic field, and he's showing, you know, which way that field is pointing at around the wire. But when you have one side of the wire against the other, they're pointing in the opposite direction. If this one, from your point of view, if this one is counterclockwise, the fingers here are clockwise. They're opposite. Once you turn the wire around, see, if you go with your hand all around, when his hand is over here, it's facing like this. When it's on the other side, it's facing like that. The fingers, you know, they're curled in the opposite direction. So you have to explain, you know, if the magnetic field here is clockwise, here it's counterclockwise. That's another property we will have to explain here. You cannot get away and say, well, I cannot explain this part, but I'll explain some other part. You have to explain each one of these properties. And here we have another property. If we coil that same wire, sufficient winding, you will find that the field goes through the inside and comes out the outside. They blend, they turn into this flow, and it goes around the coil. It goes on the inside of the coil and comes on the outside of the coil. That's what we will have to explain this phenomenon as well, this property. Okay? And we have to explain how that coil turns into a magnet itself. The magnet has the same property as a coil. The field goes through the center here and out the outside. That's the direction of the field. Okay? We're talking about the direction of the field. The field goes through the center of the magnet, comes out on the outside. We call the north side where it comes out, the south side where it comes in. Direction of the field. Okay? Here I put two tanks, army tanks, and the wheels of the tank, you know, they're mirror images in this case. One's running against the other. And this is exactly the flow of the field. It goes through the center of the magnet and out the outside of the magnet. So this is mimicking, this is an illustration we just saw. Okay? It's another way of presenting. Here's another way of looking at it. You can have two wheels turning in the opposite direction, and they'll have no problem in strolling against each other. They don't like each other. They just hit each other and like push each other away. And we can't produce it here, but what if this one were to go clockwise? Would this set of gears move? You've got one coming down, the other one coming up, they get stuck. There's no motion. They hate each other. They attract each other. As long as we have them in the opposite direction, they don't like each other. But the other way, they lock into each other. You can't move either gear. Another different way of seeing this. Here's another property. We have two wires, parallel wires. The attraction the current is running in the same direction in both of them. If it runs in the same direction, the wires attract each other. If current runs in opposite direction, one comes, the other one goes, they don't like each other. They push each other away. We have to explain each one of these characteristics, these properties of wires and of magnets and of coils. Can't avoid any of them. He who cannot explain each step here has not explained how this world works. And here's another one. We have two wires, and we sprinkle iron filings around them. Two wires running current. Okay? If the current runs in the same direction, it runs into your eyes through both wires, this is the pattern that's formed by the iron filings. Contrast this with the wires running current in opposite directions, and you get, if you pour the iron filings around them, you get this pattern. Okay, and again you can see that there's a pattern very similar to what we just saw with the two gears going in opposite directions. They don't like each other, and this is something similar. This one goes this way, this one goes that way. That's the impression it gives you. Very different than the one you just saw a minute ago, which is that one. Current running in the same direction, current running in opposite directions. Those are how the iron filings get sprinkled. That's the pattern that we see. We have to explain each one of these phenomena. Okay? They talk about lines of force. They say the lines of force make up the magnetic field. What is the problem with that? The problem is that they say that the magnetic lines of force are not real. Again, they're doing physics with nothing. They're saying we use the lines of force to illustrate, but don't take them seriously. They're not there. So we end up saying, well, then what is the field? If we have a field that's producing a physical phenomena, physical influence, physical force, and then we say, well, yeah, and we can explain this with lines of force, and then we say, but the lines of force don't really exist, they're not there, then what have we learned? We haven't learned much. We don't know what's causing it still. So they say magnetic fields are not real entities in 3D space. They are a draftsman's artifice. It's just a trick that they use to explain magnetic fields. And here's another one that says there are no real lines of force. Field lines are simply a mathematical construct. That's what they're teaching. So, you know, the question is, how are we producing a physical phenomenon with, you know, abstractions? We got a problem there. We can only do physics with objects. These lines had better be real. We just need to find out what they are. And there's another problem with that, and that's that they say that that they talk about magnetic flux, that something is moving in there, but they say flux does not actually flow from north to south pole, or flow anywhere for that matter, as magnetic flux is a static region around a magnet in which the magnetic force exists. In other words, magnetic flux does not flow or move at all. So we have a flux that is not fluxing, a flow that is not flowing. And this is wrong. You know why it's wrong? Ampere, 19th century investigator, guy who did quite a few experiments with magnetism and electricity. He discovered that magnetic lines are produced by moving charges. So we have something that's moving that's creating something that's static. That's what the impression they want to give you. And that impression is wrong, and we know this because of the following. These are iron filings that are sprinkled in water. And now they put a magnet in there, and you can see little by little how the little iron filings are being collected around the magnet. Something is drawing them there. Something had better be moving. You cannot talk about a static field if the iron filings are being collected one by one close to the magnet. Something is moving. This field is in motion. In other words, the field has something that is dynamic within it, something that is moving in it. Otherwise, you can't produce this. It's slowly collecting one particle at a time. Okay? So we have to just figure out what these lines of force are. And in order to do that, we're going to contrast quantum mechanics against what I'm going to be proposing today. Quantum mechanics is a world of discrete particles. And what we're proposing in exchange is that all atoms in the universe are interconnected. Every atom in the universe is connected to all others. There's the distinction. And here I illustrated it for you. This is quantum mechanics, discrete particles, a universe of particles that each one is independent. And here we have what I call the rope hypothesis, and we'll see that why the name for that in a minute. All particles in the universe are interconnected. Now there's a difference between these two in the sense that you cannot produce the force of pull with discrete particles. Here I have a few little balls that I usually use. We have two particles. This is the entire universe. How does this one get this one to move from a distance if there's nothing else in the universe except these two particles? The only way this one can get this one to move if they're somehow connected by an elongated, extended object. Then you can get this one, you can rationalize how this one gets this one to move. You can pull on it with something in between. If there's absolutely nothing in between, you cannot produce pull. And quantum has a problem with the force of pull. They cannot explain the quantum mechanics, the people who are, who subscribe to this theory, they cannot explain the force of pull. You will never hear gravity. There's no way to explain gravity under quantum mechanics. You can only explain gravity if everything is connected. And you can explain why the Andromeda galaxy is being drawn to the Milky Way galaxy, because there's a connection there. Otherwise, we're dealing with angels, with spirits, with ghosts. If there's nothing there, we have to do it magic. Okay? So that's our starting point. We're saying there's a difference there. So the question is, what are these lines that you see there? What are these interconnections? And we're saying that that's a rope-like mechanism, and it's got to do with light. This is the standard view that you learn in high school and college of light. It's an electromagnetic wave. They just send this thing out, which is not a thing, because I don't know if you see it well here, but these are all little arrows, painted arrows. And you say, well, what is the object? What is the mediator? What is the entity that's here? And they say it's nothing. It's the undulation of nothing. That's what you get. That's what you'll see. That's what you'll be taught. No, we're saying that this is really a rope-like mechanism. We have two threads, twined threads, and that's what is interconnecting each one of these atoms here. We're saying all those lines are a rope-like, DNA-like entity that connects any two atoms. What is light? Light is the torsion of that rope. Here you see the rope twirling, and we're saying that's what light is. It's the torsion of a rope. Whereas this one is just a mathematical construct, just a nothing bunch of arrows that they paint in. They say, well, the wave moves. This doesn't tell you what physical mechanism is producing light. This one is saying there is a physical mediator. It's a rope-like mechanism that binds any two atoms. This is the famous quantum jump. They say this is how light is generated from an atom. An atom has a little center part called a proton. At the edge you have an electron. The electron jumps back and forth. And when it falls to a lower energy level, a stream of particles called photons comes out. And when it rises to an energy level, it absorbs a stream of photons. So the atom just pushes photons out and pulls them in constantly. This is another version. This is with the wave. The atom again pumps back, the electron pumps back and forth, and a wave comes out. Goes off to nowhere. And we're saying these two images are wrong. This is the incorrect way of looking at of nature. What we're saying is that there are two atoms. Here we chose two atoms. They're interconnected by a rope, And as they expand and contract, they torque the rope. Light is that torsion, is that signal along the rope. That's what we're proposing in exchange. Okay? How does this produce, what does this have to do with magnetism? We have two atoms, and we're saying they're connected by a rope. And the rope, one of the threads comes out loose, starts twirling around. Starts twirling around. What happens if we have more than one atom? We have a row of atoms. Well, then we have a wall of threads going around. Okay? So we have a series of atoms. They're all connected by this rope. One of the threads comes out loose. Starts twirling around. We have a row of atoms. Several of the threads come out loose and they swing the threads around. Well, the first thing we can explain with this, just so far, with this setup, is what I showed earlier here. We can explain this field that goes around a wire. Instead of electron flows, little beads moving along the wire, we have the atoms, the electrons spinning the threads around the wire. So now we have simulated this in a different format. We don't have electron flow. What we have is the turning of atoms. They're spinning, and they're spinning the threads around themselves. Those threads, those lines of force are threads, and we're saying these are physical threads. They produce physical effects. So we have at least mimicked this in a different way. We're saying there's no flow of electrons. What we have is the turning of atoms. They either turn clockwise or counterclockwise, doesn't matter. But whichever way they turn the whole wall of threads. Okay? Second part, we're going to explain what happens when we coil the wire. We take this wire, we turn it around, and now we coil it. In other words, what we've done is this, right? In this direction. And the ones at the top have a different direction as the ones at the bottom, just by turning. Here they were like that, right? With the my thumb will be pointing this way, but the current should be like this, right? I'll forget about this thumb here. They should go like that. But what happens when you turn them around? Well, they're in opposite directions. You see that? The fingers are in opposite directions. So the ones at the top, the ones that are colored violet, are going in the opposite direction of the ones at the bottom. They're in opposite directions. Simply by curling the wire. Now they're spinning the threads in this direction. The other ones are spinning in the opposite direction. But look at the interesting part. They run the force right through the center. You know, if one is spinning this way and the other one's spinning that way, the force is through the center of the coil. And that's what I'm showing here. Okay? So we now have explained the second part. In other words, we at least have been able to simulate what we see here, where we coil the wire. Okay, we coil it, just give it one coil, and this side is now going to be turning opposite that side. We have at least mimicked that. So far we have explained these two phenomena. Okay. Let's see if we can explain the third one now. We take this coil, and we have several of these coils. Think of this as a cross section. It's a coil, but we cut the coil in half. So what you're seeing is half of the coil. The top ones spin in this case it's clockwise. Here it's counterclockwise. They should be opposite. The force is through the center. The force is going in this direction. Under the current labeling that we use, this is the north part of the coil or the magnet, and this is the south part. The force goes in through the back, that's the south part, comes out the front, which is the north part. Okay, so that's what we're seeing here. And this mimics or simulates quite well the coil that we saw earlier. The force runs through the center and comes out the outside. It's mimicking exactly that, you know, what we observe in the laboratory. Okay? It's mimicking that. It's not this way, that's why the X is there. It all blends together, and now the force goes through the center of the coil, comes out the outside. So we mimic this as well. We simulated these three properties of coils so far. If we have the atoms spinning and moving the coils, the threads through the center, coming out here from south to north, we can see what the flow looks like inside a magnet. If we were to sprinkle iron filings around it, it would take that pattern, exactly the pattern shown here. The bottom one goes counterclockwise, the top ones go clockwise in this case. And that also simulates what we saw earlier, which is this, where the coil turns into the magnet. If we were to sprinkle iron filings on top of a magnet or on top of the coil, these are the patterns that you would get with either one of these two mechanisms. Okay, without the flow of current. What you get is simply atoms turning in place, swinging the threads that connect them. And now the question is, how does this produce attraction and repulsion? How do we get from this mechanism that I just explained, the flow, the turning of atoms, which swing threads around, real threads, those famous lines of force, that causes some kind of push. How do we turn that now into attraction and repulsion? How does a magnet work? Now let's begin by showing the simple mechanism. Let me show it here. There's a little device I made last moment. I thought it'd be interesting. Very crude device. I'm sure the new generation will come up with something better than this, something automatic, so we got to leave something for the new generations. And what this does, it simulates rope jumping. You're jumping rope, you're skipping rope, and that's what it does. Very simple, crude thing. It turns around and it skips. So in this case, from your point of view, they're both going counterclockwise, right? Now what happens if one of these comes down while the other one tries to come up? Well, they tend to grab, they tend to pull on the other one. On the other hand, if we send one clockwise, this one is still going counterclockwise, they tend to clash and push each other away. They don't like each other. So it's not the same thing for two things to go in this direction and clash, than for both of them to go in the same direction, one pulling on the other one. And that's what this is simulating, okay? Let me now show it here. We have two brothers. I call them Axel and Rod. And Axel, the blue guy, is spinning his rope counterclockwise. And Rod is also spinning his rope counterclockwise. And they get tangled, they're too close together. So what happens? When this guy's rope comes up, it grabs, it clashes, it picks up the rope of Rod as his comes down. So if they're both going in the same direction, they got a problem. In the sense that they interfere with each other and one pulls on the other. There's the mechanism of pull that we're going to explain. How about push? That's pull. Now we're going to look at push. We turn axle around, and now the ropes collide. They hit against each other. They don't like each other. So now we have push. Now notice this pretty much resembles the pattern we saw earlier of iron filings sprinkled around two current-carrying wires. Here we have the two wires. They're both moving in the same direction. They're both counterclockwise. They're spinning all the threads in the same direction. Okay? And as this one comes up and this one comes down, they pull on each other. The closer the wires are together, the more threads that intervene. The more threads that intervene, the faster, the stronger the pull. And you will notice, well, maybe you won't notice it just by trying two magnets, but they've done it in the lab where you can see the speed. It's exponential. At first, the magnet starts attracting, you go, and they go faster, faster and faster and faster as they get closer together. Why? Because as they get closer, more threads intervene from more atoms. They're closer together, more threads grab onto each other. Okay? How about push? They're going in the opposite direction. They don't like each other, so they push each other away. The closer they are, the more atoms that intervene, the more threads that intervene, the harder the push. The farther they are out, the slower it gets. Why? Because fewer threads are involved. Here we have a simulation of both of these. Here we show how they attract by moving, trying to illustrate there how a magnet is attracted to another. We turn the magnet around, as long as we turn it in the same direction and we still have north against south, as it's called, there still will be attraction. But what happens when we turn one of the magnets completely around? Well, now they don't like each other, they hit each other and they push each other away. You see that? So let's look at that again. The attraction, they're both moving in the same direction. One collects the other, pulls it in. Whether you turn the magnet rotate it, as long as you keep the same face, nothing will change. There still will be attraction. That's what we see, and that's what we're simulating with the threads. In order for there to be repulsion, you have to turn it completely around. We have north against north or south against south. Now the threads are going in the opposite direction. Now they're hitting each other and pushing each other away. So we have simulated what we see with magnets with the threads. No magic, just threads that we can't see, that's all. Here's the pattern of two wires carrying current in the same direction. And we can see that here, we see the same patterns. We see the circular patterns that are formed by it. The closer the two wires are together, the threads encompass both wires. And so if we were to sprinkle iron filings around these two wires, we would get that pattern. That's the pattern you expect because they're moving in the same direction. What happens if we turn one of the wires around or change the current flow? Well, now you get something like this. You get the flow of current, the flow of the threads in this case, right? Moving like this, they don't like each other. And if you sprinkle iron filings on those two wires, you're going to get that pattern. So again, this tends to point to the flowing of threads, the movement, the scanning of threads. Here we have the four corners of a magnet. I don't know if you see the red lines in the center. That's supposed to be like the center of the magnet. I'm trying to give you a 3D image there as best as possible. The south side, the threads go in. North side, the threads come out. They're flowing all around the magnet. If we were to look at just the square magnet, through the center here, right? That's the center here. The threads are moving through the center, coming out, over, and into the center again. So it's like the tank that you just saw a minute ago. One tank is moving that way, the other tank is moving that way. Okay, so that's what you're seeing there. And again, those are the, if you sprinkle iron filings around a magnet, that's the pattern you would get. That's the classical pattern of a regular magnet. We're saying essentially that a magnet is divided between not north and south. It's divided between top and bottom. Any magnet, that's why we can't find a monopole. They've been trying to look for a monopole for years. There's no way. You need two to make a magnet. You can't do it with one. Why? Because the top ones, the threads are moving around the magnet, going through the center, and colliding against the ones that are going in the opposite direction at the bottom. So I can cut this magnet in two, and I'm going to get the same result. No matter how many times I chop it up, I'll never get a monopole. Because on the top, they move in one direction, on the bottom, they move in the opposite direction. A magnet is not divided between north and south. It's divided between top and bottom, up and down. Now it makes sense. Now we can explain, if we put another magnet here, which I'm going to do now here, we can explain why magnet rejects the other one. You can see what's happening here between the magnets. This is the north side, that's the south side. That's the S there, I guess. you can see how they're clashing. The threads are moving in this direction at the top, in this direction at the bottom, and they're colliding against the threads coming from the bottom on the other magnet. That's why they don't like each other. They either attract, in this case they're attracting, and you can see that right here where the juncture is, well, two are coming in, the other ones are coming out, and they're grabbing onto each other. That's what they're doing. That's why they attract. The threads are moving here, this way, and here they're moving that way. Well, what happens when we turn the magnet around? Well, now you can see they're colliding. They don't like it. And all we did just turn the magnet around. But it's the physical threads that produce that. There had better be an object there, or we're all crazy. With this, we can explain how magnets attract each other in both directions. When the magnets are facing, in this case, red against blue, they're moving in the same direction. One comes up, pulls, and pulls it in. If we rotate it sideways, no change. You can see that the same effect happens. In order for them to repel, you have to have turn the magnet completely around so that it's facing the other direction. Now they collide. So it's the threads that underlie this phenomenon. Okay? Here we have the hosts, and they generously provided their castle where we are performing this physics conference, and we want to kind of reward them with a little something, at least from my part, and I'm going to give you this. So that you can play. You have to handle this one, and he handles that one. Okay. Okay. Every night, you turn it around.
That is so cute. Hey,
You'll have fun all night.
What an idol.
So you learn how the Rove hypothesis works.
I've always wanted something like that.
I don't agree.
Thank you. Thank you.
DC.
I'm sorry?